Dear ladies and gentlemen, I want to welcome you to my webinar, Measuring Inside and Outside with our Computed Tomography Solutions. So let's start with the webinar. Here, a little outline first. First, at the very beginning, I will tell you about what about X-ray, the principles of computed tomography. I will give a little introduction to our CT product line, and then I will start with CT applications. So to bring us all on the same knowledge base, I prepared a slide about what is X-ray. So getting started with X-rays. In principle, X-rays is part of the spectrum of electromagnetic radiation. So talking about electromagnetic radiation, I think everyone knows about these radiation. If we start at home, we do have electric devices such as TVs. Maybe I think everybody is familiar with, and TVs operate with voltage, and TV operate with frequencies. So we need, in principle, we need two things. We need a voltage and we need a frequency. At home, we have quite low frequency. So frequencies at home are quite 50 hertz or 60 hertz. But that's not all. So that's just the beginning. If we go to higher frequencies, we come to mobile phones, for example. We come to airplanes. Even above that, we have microwaves, for example. And then if we go even to higher frequencies, then we come to the visible light. So the visible light consists out of infrared, which is the lower range of the visible light. And the upper range is the ultraviolet part. And the visible light is the only part of the electromagnetic spectrum that can be expired, that can be perceptible by human senses. And then above that, there comes the X-rays. So compare it with the voltage again. At home, we have voltage about 110 volts or 230 volts, depends on. So in the X-ray region, we have 1,000 times more voltage than we have at home. So we're talking about kV, thousands of volts, and even that, the electromagnetic spectrum does not end at this range. So beyond the X-ray, there comes more. So in the range of billions, millions, and billions of voltage, there we come to power plants, nuclear power plants. And the main difference of the spectrum of electromagnetic wave, including X-ray, and the power plant is, technologically speaking, that if you switch off the power connector, the main switch, then the spectrum, the lamp, let's say, goes off. And that's the difference with in the nuclear power plant. If you switch off a nuclear power plant, then there's still materials that do radiate. So that's the main difference. X-rays is more than the microwave. So if you switch off X-ray CT, or if you put your part out of an X-ray CT, there is no more radiation at all. So X-rays is quite more like a microwave or a visible light than it is to the nuclear power plant. Okay, so now that we know what about X-ray, we can have a look to the technological application. So one application is computed tomography, the main focus of the webinar. So let's talk about the principle of computed tomography. On the left-hand side, we do have an image of the inside of such a system. So such a system consists of an X-ray source where the radiation is emitted. Then it consists of a detector, and the object is placed in the middle of that. And in 3 dimensions, the smallest element is a volumetric pixel. So this is an artificial word, and that's an voxel. So that's the smallest element. And the whole thing that comes out in the memory of the computer that we call voxel or volume data. Yeah, so that's about the scan. Let's have a closer look into that. So if we talk about the result, the image stack, the volume data, if we cut that volume data in an arbitrary slice and have a look of it, then we see here on the left-hand side, that's an image, and the image consists out of gray values. So the gray values range from black to white, and the CT recorded the object density, the materials density of the objects inside the scan volume, and it codes the density into the gray values. So the lowest gray value, that's black, that is the material with the lowest density, that's air. And the highest gray value, well, it's the part, this is the highest density, and this is the part. And therefore, we already see our very first application of that technology. If we see that images, then we can see, well, we can see inside the part, and we can do non-destructive testing. We can see that everything that should be inside the part, that is inside the part. Yeah, so that's the very first application of CT and the whole process. Okay, so let's go further. I will present you our exact product line. So this is a whole CT family. Starting from the left-hand side, we do have a tabletop system that's split into 2. So the one is the first one, begin with the first one. That's called an exact S for small 80. 80 stands for the kV of X-ray energy. So this is a basic entry system. Then comes the next step is the S130 with 130 kV. In the middle, we have our workstation. That's our new Exact L 225 kV, which is a very powerful system. On the right-hand side, we do have our flagship range. That's our Exact U in the flavor of 225 kV and 300 kV. Into detail, our tabletop system has a maintenance-free X-ray source, very powerful X-ray source for that size. The scan volumes is 85 millimeters times 40 millimeters, which is perfectly suited for micrometrology application. We do have it with a fast or a high resolution detector, and when we want to use it as a metrology system, as a coordinate measurement device, then we have to talk about accuracy. The accuracy is stated in a German guideline called VDI 2630. And so we're talking about 70 microns of accuracy for our tabletop system. The system is equipped with an operating software, WM control. We do have an evaluation software, which is the point master for CT. And last but not least, optional, as we talk about metrology in terms of the application, then we can equip it with the WM Quartz. Into detail with our new EXACT-L. So it's a mid-class CT workstation, also with a low maintenance, high power X-ray source with 225 kV and enormous outstanding 1,600 watts of power. Quite a large scan volume, a robust and fast detector with also quite a good resolution and a very good accuracy for that system. It's also equipped with the same software. So talking about operating system software, talking about evaluation software, the Point Master, and optional again the Quartz. So the flagship is the EXACT-U. It's the most compact 300 kV CT system on the market. It has a high power microfocus X-ray source with 350 watts, a very large scan volume of 330 up to 700 millimeters, and an ultra high resolution detector with 4K pixels. So I think you know that expression. Everyone talks about 4K TV. So you can compare the resolution of the detector with a 4K TV, which is very, very cutting edge technology. The accuracy is better than 15 microns according VDI 2630. So also the equipment, software equipment is the same as on the other system. So as I think you can imagine that such systems produce an enormous amount of data. We do have also a PC workstation for data evaluation, which is a high-end PC with 6 cores, enormous amount, 120 gigabyte of memory, terabyte SSD solid state drive, terabyte hard drives, quite fast graphic cards, and what is important for the speed, a 10 gigabyte network. So the PC workstation can be equipped again with the Point Master for CT, the Quartz, and optional also a VG Studio software for evaluation. So talking about evaluation, we have to talk about software. So let's have quite a look on the CT workflow. We talked about CT scanning. What comes out, the volume data. And in the CT workflow, the volume data is automatically transferred in the memory of the computer to the Point Master for CT, to our evaluation software. So this goes fully automatic. So if the scan is finished, we can start with the software evaluation. In the Point Master, we can do many different kind of evaluation. We can do, for example, a defect analysis. We can do a wall thickness analysis, actual nominal comparison, optional, depends on the application. The software is quite modular built, so we have the possibility for an option for a process called reverse engineering, rapid prototyping, reverse engineering. And there is an option for compensation of shrinkage and distortion in the molding process, for example. So if this is not enough, there's also the possibility for the quartz. So I don't know if you're familiar with the quartz. So the quartz is normally used in our in the WENZEL product line at all to drive the tactile coordinate measurement machines. So we do use the same product here, the same software, the WM quartz, but we do not probe our CT data by probes, by Ruby spheres. We do probe it in the memory of the computer in a virtual process. So we call this virtual coordinate measurement, VCMM for the machine. So, and therefore we communicate with the point master, and then we have in addition the possibility of tolerancing, positioning, orientation, form and size, and this is our automatization interface for a fully automated process. Yeah, so this is the CT workflow. So and now, if we know about the workflow, let's have a look into our application. So our application are manifold. So we talk about application parts that can be scanned. We talk about molding parts. So it does not depend on size or on materials. So here quick examples: aluminium, in the range of aluminium, in the range of plastic. So the application in non-destructive testing. So in components, multi-components, parts, and so on and so on. And then I pick some now. I will pick some application here. So let's have a look. As application example, in the very first, there may be an assembly inspection, which can be a sort of non-destructive testing. So let's have a CT image, which is a very projection image, quite similar to the dentist. So this is only one radiographic image on the left-hand side. And from this one, we can check if everything that should be present to guarantee the work and the operation of the part that is present in the part. So this is a sort of assembly inspection. So is the part going to be functional in an assembled state? Sometimes it can be answered just in one X-ray image. So if this is not enough, we can begin with a CT scan with the 360 degrees rotation. And then we come to our 3D volume data. And therefore, then we can go into deep the part and can also perform metrological application. Yeah, so that's one. And the first thing, the assembly inspection. So furthermore, in a material science, we can check what about the quality of the material. Is it as it should be, robust? Is it the materials need to be fabricated more and more with low cost? So these are questions that have the material science. So and then there we can scan parts there, and when we look into the parts, we can study their structure, their inner structure. So at this application, we see that the parts differ in density. So we do have a micro structure in the part. So and these are composite parts, for example. And if we look inside, then we see if the material will fit as it should, as it's designed. Okay, so one example in the aluminium die cast here. There's always a question about the product optimization and the die cast process. So how should the process and in the manufacturing be changed that we have high quality products with less and less time and less effort? Yeah, so this is a typically task in the die cast process. And if we perform a CT scan with that part, we can do a shrink hole analysis, which also is a fully automated process. And the volumes of the shrink holes are color coded, and therefore we can answer if this part will also function or will it break maybe if the shrink holes are too large. And this is for optimization of molding parameters and form parameters. Furthermore, lately we're talking about additive manufacturing, and so this is a great application for CT because in the additive manufacturing we have to optimize the additive manufacturing, which means that is a complete process about building the part, about sintering the part, and processing, finishing the part. So, and as the additive manufacturers parts tend to be more complex than parts that are fabricated by traditional manufacturing. So this is a perfect CT application. So here in this application, we scanned a part, which is in fact the same part. One freshly, in the first time, first was freshly built, and then at the end of the process, when it was sintered and finished. Here we can do an is fine, and if the part of the quality, if the quality of the part is good. Okay, so putting it all together, I prepared two videos. The first video is a video about the PointMaster software, PointMaster for CT. So just a few seconds. So few words about the PointMaster. Here we have already imported our CT scan data of the part, and we do a quick inspection of the surface of the part. So the PointMaster is a very modular software. It can be configured for any kind of application with the modules. Here we see some application now. In this case, we have cuts. We can perform virtual cuts through the part and can do a dimensioning here of the inner geometry of the part. Here as example a circle, but there can be circles, angles, distances, whatever. And there is the also points can be measured, so point-to-point distances here. So the cuts can be performed in any kind of orientation, and they are virtual, so nothing happens for the part. So it's a 3D software with a very intuitive interface. Now, in this example, we do see the alignment process. The alignment process is always the very first beginning of a virtual measurement, because we need for the alignment, we need a nominal description, which is computed with a model of the part from the constructor. In this application, we see this green coded, so this is the theoretical model. On the red one is the part itself. So with just few clicks, the part is aligned to the cut model, depending on the description on the drawing. So now we have performed an alignment here, and from that on we can do measurements related to the CAD model. For example, here the first measurement is always a so-called nominal actual comparison. So everything, this is the result is color coded. So everything that one can see here, what is red colored, is there is too much material. Everything where is the blue color appears there is too less material on a part. So this is a 3D overview over the whole part, and there's always the interest also what is locally done here. So one can again perform here virtual cuts through that part and look inside with threads for here, for example. What about the deviation to the cut model inside? Here that little whiskers here, and even more locally, one can click on each point and have here a point deviation as it would be on a real CMM here. Okay. So now I talked about the metrology and using the WM Quartis. So the WM Quartis is a software that normally, I repeat here, that used to drive a tactile CMM. And now you will see the how our virtual and here in this video we can see how our virtual CMM interface works. So that's the Quartis the user interface. The CAD here is already imported, the CAD model of the part, and by just one mouse click the software applies many points, probing points on that CAD model. And by just one click on that green button here, the points are already collected from the scan data from the real part, well, in the memory of the computer. This goes quite quickly as it is a virtual process. So normally on a CMM, it would take quite a long time to sample hundreds or thousands of points. Here, this goes in few seconds. And also this software is very intuitive in operation. You just click on the geometry and click on the point distribution you want to set on, and then the software does this fully automatic. So this is a sort of live measurement or real measurement mode on as it would be on a CMM, but there are also other modes in the software. Yeah. So this was a live, a real measurement, online measurement, one would say, on geometry primitives. The Quartis has also the possibilities for free form surfaces. Here, this in this example, is a turbine blade shape here that can be evaluated. So there are also cuts through that turbine blade, and the Quartis samples point of the contour of the 3D contour, and then there can be applied a tolerance band through that contour. Everything that is green, that's inside the tolerance. Everything that's red here in this example is outside the tolerance, which is the typically turbine blade inspection. So this was the live measuring mode. Now there is the programming mode. If you have a repetitive task and you want to automate, this is the automatization interface with the Quartis, and you just everything what you did, you just record it, and there's a live recording function, and this goes into the program, which is you see the section, the window on the right hand side. So by everything it clicks, it adds a new step of the program. So step by step you build the program. There is no problem with inner geometries, and now as we programmed the Quartis, we just make one single click, and the program is now executed, and it goes through every line of code here, and within few seconds there is a fully metrological inspection of the part, and the report is generated. So the report can be saved as PDF or can be saved in a database which comes with the Quartis, and this is a fully qualified metrological inspection. Yeah, and then we see the other interface. So the virtual interface on the side of the point master, as the program is executed in the Quartis, in the memory of the computer happens on the part the virtual probing, and that's the green points that one can see here that sample the parts geometry. Okay, so thank you very much for your attention. And I think I hope that you liked the webinar. Please, you can meet me tomorrow on the expo. I'm on the chat, and I would like to chat with you. So thank you for your attention again, and have a nice day.